So great. So it's the first time seminar of this academic year, and we're happy to have Gwyn Bellamy from the University of Glasgow. The title is Koszul Duality on bionic symplectic varieties. Gwyn, please.
Okay, well, thank you very much for the invitation, and especially thank you for being accommodating with the time difference. It's much appreciated. I have to confess, I tend to go a bit quickly with these slide talks, so please do stop me or slow me down if you have any questions. Yeah, so this is based on recent joint work with Chris Dodd, Kevin McGerty, and Tom Nevins, but it's a really sort of offshoot of old work we did about 10 years ago now. Okay, so I'll try to motivate the work with some sort of background on localization for quantizations of symplectic singularities. So I guess the general idea in geometric representation theory is that you have a certain class of algebras whose representation theory you're interested in studying. So there's some examples here. So you could just take some semi-simple Lie algebra and consider modules for that Lie algebra. So let's say that they factor through some primitive central quotient of the enveloping algebra. Or the case that I care about most are certain algebras called rational Cherednik algebras. So in this context, I guess one should take spherical subalgebras of these, but it doesn't really make much of a difference. There's also things like finite W-algebras in the sense of Premit, or you could take quantizations of Nakajima co-varieties. So you want some sort of uniform way to...
Yeah, I have a technical question. Is it just on my screen that your picture or former picture, it's abstract the slides, or it's for everyone?
Oh, maybe that's everyone. Is this thing?
Yeah, maybe you can move it somewhere.
Yes.
Yeah. Okay, great.
Oh, is that better?
Okay.
Yeah,
much better. Okay.
Great, thank you. Yeah, so we want some sort of geometric uniform way to study algebras like this. And I guess this sort of fits into Okunkov's sort of general program of symplectic representation theory. So in all of these examples, what one has is a quantization U of some affine symplectic singularity. And so what this really means is that our algebra is filtered, and when you take the associated graded, you get functions on some symplectic singularity. And so X is affine and has some symplectic form, holomorphic symplectic form on the smooth locus. Okay, and so what we want to do is we want to try to study modules for this U via some sort of localization equivalence. And so what we do is we pick script X to be some symplectic resolution of our singularity. So this is a smooth symplectic variety and some form of sheaf of algebras, which I'll write W, on this smooth symplectic variety in such a way that taking global sections gives you an equivalence between sheaves of modules for this W and representations of your original quantization. Okay, so I'm thinking some sort of version of Beilinson-Bernstein localization.
Yeah, I understand, but since it's sort of introductory, a bit of philosophical motivation. So in representation theory, people often are more specific about classes of representations, like you can consider finite dimensional representations, or you can consider highest weight, like category of O, like in Beilinson and Bernstein. But there are many others. So what kind of representations do you have in mind?
So in fact, in this case, it's going to be for you all representations. So no restrictions. So not even finitely generated. Oh, well, actually, that's not true. I mean, later on, I want them to be finitely generated. So for W, that would be coherent modules. But I'm not going to restrict to highest weight or anything like this. If you ask me again a bit later, category O does implicitly appear, but not explicitly.
Okay, thank you.
Okay, so of course this is all very vague. So what do I really mean? So the question is, what is this sheaf W in general? Okay, and so that motivates sheaves of deformation-quantization algebras on these smooth symplectic varieties. So since the script X is symplectic, the sheaf of functions on this variety, it's a Poisson algebra. So it has a Poisson bracket. And a deformation-quantization algebra, so DQ algebra, script A, on X is going to be some sheaf of algebras over formal power series in some variable H bar. And we want these to be nice in an appropriate sense. So they should be complete and flat over this formal power series. And we want them to quantize the Poisson structure. So that means that when you quotient out this variable H bar, you recover functions on X, but as a Poisson algebra, okay? And the point being that since we're flat over H bar and the quotient is commutative, if you take the commutator of any two elements in A, that's going to be divisible by H bar. And so you can divide out and then take the quotient again. And this is a well-defined bracket on the quotient algebra, and you want that to be isomorphic as Poisson algebras with functions.
Just a quick question. So the deformation algebra A will have automatic filtration. So
yes.
Okay.
Yeah.
So A is
yes.
Yeah.
5 powers of H. Yeah.
Mm.
Yeah. Thank you. Right, and so in our context, a key result is the theorem by Bezikhavnikov and Koledin that says that for symplectic resolutions of affine symplectic singularities, there's an explicit parametrization of all possible deformation-quantization algebras, and they're given by second cohomology of the space with, by formal power series in H, but with coefficients in second cohomology of your space.
Gwyn, I have a question about, you say Bezrukavnikov, Koledin, but there is this general story of Kontsevich, which for arbitrary X, it gives you a sheaf of algebroids, but for some special X, whatever, Carly X, which is symplectic, it gives you indeed sheaves of algebras, and for general reasons, it just parameterizes by H2 effect. I mean, like in your slide. So what's specific about this Bezrukavnikov Koledin, and why it is important to have symplectic resolution here?
Oh, I see. So, well, I guess their proof is quite different. So it's by, I guess, sort of jet schemes.
No, I mean, their proof is pretty standard. It's like, if you have a local model, you have this Harishchandra pair or group. I mean, but the proof is different, but the result, is it a special case of Kontsevich, or it's something independent and it cannot be obtained from general theory?
Well, I'm not expert, so I suspect it could be obtained. I mean, I guess the way I saw it is the situation is more specific and somehow easier, much easier than Kontsevich's general result. So I think my guess is that they don't require Kontsevich's result. It's
they don't. But for symplectic manifolds, either it's infinity or complex analytic or even algebraic, there were kind of independent methods. Indeed, before Kontsevich, but it's a special, so it's not something which people could not obtained by other means. Simply with
No, I
Karpov and
suspect not.
Kaledin wrote it. Okay, great.
Yeah.
Thank you.
I mean, the result is a bit more general than symplectic resolutions. They have some notion of admissible, which is essentially saying that the first and second cohomology of your of functions.
Yeah, it's exactly as in Kontsevich paper of 2000. It's the first and one condition guarantees that you have a sheaf of algebras, and actually there is another one which says that you have a global algebra. Okay, anyway, okay. Yeah, I understand. Thank you.
Yes, so I'd say a special case of Kontsevich's setup. Okay, so going back to our original quantization U, we really need to somehow get rid of this additional parameter h bar, this four-ball parameter that we introduced. And so the way one can kill this is by introducing a certain GM action. So I'm going to assume that functions on my original singularity are n-graded. So in fact, this is always the case for us because functions on X are the associated graded of the filtration on U. So it always has this n grading. And I'm going to assume that degree 0 is just the complex numbers. And the Poisson bracket has strictly negative weight. So geometrically, we can think of this as a GM action on my singularity X. And this action will always lift to the symplectic resolution then. And so I'll call this the elliptic GM action. Okay.
Elliptic means that L is positive, yeah.
Exactly, yes, yeah. Okay. So X is a cone, it's an affine cone. Yeah. Yeah, well, and the Poisson structure has that weight, yes. So one can then look at GM equivariant deformation-quantization algebras on the resolution. So to do so, one gives h bar weight L, so strictly positive weight. And it was sort of checked by Losev that in this case, the equivariant ones are parameterized by second cohomology on the nose. So giving me the equivariance kills H in the classification. And what we then do is we formally invert H or H bar. And that gives us the sheaf we want, which is this sheaf of deformation quantization parameters, but now over the field of formal power series in H bar. And in all the cases I mentioned above, what happens is when you take global sections of these sheaves and you take invariance with respect to the GM action, you recover your original algebra. And this is as a filtered algebra. So going back to the question about filtrations, because A has a filtration by powers of H, so does W. And when you take the global sections, that translates to the standard filtration then on your quantization.
Should I think of this lambda as a kind of analog of the central character for the enveloping algebra?
Oh, you should, absolutely, yes. So if one identified this with a Cartan inside your simple Lie algebra, then well, you know, up to shifts conventions with shifts, this is precisely the central primitive quotient of your enveloping algebra.
Oh, okay, good.
Yeah, exactly. Okay, so in that case, what one implicitly recovers is that these are really corresponding to twisted differential operators, but now they've been micro-localized under the cotangent bundle. Okay, so what we want to consider in this paper, in this talk is coherent W modules. So W itself is a coherent algebra, so it makes sense to consider coherent modules for them. And I'll work with right W modules, and they'll always be equivariant for this elliptic action. And often in the literature, these are called good W modules. Okay, so there exist various sort of localization results then in the literature that generalize Beilinson-Bernstein. There's a generic one by Braden, Licata, Proudfoot, and Webster that says that for generic choice of your parameter lambda, abelian localization holds. So if you take global sections of a coherent W module, take its invariance, then you get a finitely generated module for U lambda, and this is an abelian equivalence. And there are also derived versions of this, which hold, of course, more generally. And the expectation is actually that derived localization will always hold, provided your quantization has finite global dimension. And this is known to be the case in many, many examples now. So just to mention in passing, there are also some very precise conjectures by Losev on what exactly is the locus inside this parameter space where abelian or derived localization holds. So again, this is known in many, many cases.
I try to understand the coherent. Coherent means because any W lambda module will give some as a sheaf on X, script X. So coherent means as the
because
the sheaf on X is coherent.
Yes, it means it's locally finitely presented.
Yeah, so coherent as a sheaf on X, which is coherent, and at the same time it's a W lambda module, right?
Oh, no, you have to, no, I understand. So you have to be careful here. So W itself has no O structure. So it's very different from D modules. So if you have a D module, it's a module over the ring of differential operators, but you can also restrict to O.
That's
so
right.
You can talk about quasi-coherence and so forth. But O is not a subalgebra of W in any sense. So it really doesn't make sense to talk about O structure of a W module.
But even for D modules, a coherent D module is not the same as coherent O module with a D module structure, because
Yes.
the latter are just bundles with connections. It's a very simple thing.
Yeah.
Okay.
Yeah. So it's a bit, it's different. Yeah. Okay. So before we get to the sort of main setup, I just need a tiny bit more geometry. So we're going to add in an extra ingredient to this setup. So I'll always stick with the situation where we're symplectic resolution of this affine singularity with the elliptic action. But now I'm going to assume that there's an additional action. So there's a second GM acting, but this action is going to be Hamiltonian. So it's going to fix the symplectic form on script X. And we call this bionic, just because there are these.
Yeah, why?
Why? Well, the honest truth is that Tom liked this, like the sound of this.
Because
I
it
have to
looks
admit, so
scary. Yeah, in the title of your paper, it looks scary. Some new symplectic, but I think that I saw something like that, like in this old paper by Ben Webster with many co-authors. Yeah.
yes.
Yeah, so it's pair of two actions. One rescales symplectic structure, and the other one preserves. Yeah.
Exactly. Yes. So it's the same as the setting. And I have to admit, they don't use this term. So I think it's only us who use the bionic, but it's been considered many times before, yes. And Losev, for instance, also has papers on this. I mean, the key point is, which is going to be slightly implicit in what I'll say in the rest of the talk, is that when you have this additional Hamiltonian action, there's a natural geometric category O that one can define for these modules over these W lambdas. And certainly when abelian localization holds, this is known to be a highest weight category then. And so it's a geometric way to define category O. But that won't explicitly appear in what I'll say. Yes, so you can ignore this word bionic if you're familiar with this setting already. Yeah. Anyway, so all I require is this Hamiltonian GM action, and of course it should commute with the elliptic action. And the other key requirement is that when you look at the fixed points on X script under both of these tori, it should be a finite set. Okay. So it turns out actually for the elliptic action, you don't need to require this because you can always twist the action to force it to be true, but you do need it for the Hamiltonian action. Okay, and the key point for us is that when you have a Hamiltonian action H, it defines for you, or it specifies a Lagrangian inside your symplectic variety X, script X. And so what you do is, I mean, this is, I guess, kind of standard in real symplectic geometry. You look at all those points in X where the limit as rho goes to 0 under this Hamiltonian torus exists. So you don't shoot off to infinity. And because the action is Hamiltonian, it's easy to check this is a Lagrangian. And moreover, even though this lambda is very badly behaved in some sense, it's essentially never smooth, has many irreducible components, and so on. What you do get, though, is it's stratified by the fixed points of this action, and each one of these strata, so they're just defined to be the set of points X, such that the limit is a particular fixed point. That's just a copy of affine space in our case. So that's a smooth Lagrangian sitting inside X.
Yeah, let me ask you kind of general question. So that's kind of a complex Lagrangian skeleton, and you use only fixed points of the action and the cells which are attracted to these points. But you know, this Kunkov also introduced this more general setup, it's called stable envelopes, where he consider points which are attracted to those and which are attracted to those, more complicated thing. Do they appear in this geometry? I mean, in your story, or?
I guess the short answer is no. I mean, it's possible that you could push the technology. I mean, the point is, you know, if your fixed point loci are just isolated points, then these Lagrangian pieces, of course, are much simpler. And that really reduces to, well, you'll see later on, is more or less reduces to this case of considering D modules on affine space. So possibly one could generalize this to the setting that Kunkov considers, but we didn't. It's not entirely clear that one could, but yeah.
Okay, thank you.
Okay, thanks. So just to give some examples, so I guess the sort of classical example is I could take a simple connected algebraic group and some parabolic subgroup, and then my script X is just the cotangent bundle to this. And I guess to get the Hamiltonian C star or GM action, one would choose a maximal torus inside G and a generic one parameter subgroup inside that. And that would give you a Hamiltonian action. I guess the sort of motivating example for us is if you just take a Kleinian singularity of type A, so a quotient of C2 by a cyclic group, you can take its minimal resolution, so that's just some smooth symplectic surface, and take the Hilbert scheme of n points on this surface. Again, that's an example of a symplectic variety that has these commuting GM actions on it. So other sort of classes of examples, you could look at hypertoric varieties. So these are Hamiltonian reductions with respect to tori, Nakajima equivarieties, Slodvy slices, or these slices in affine Grassmannians. Now, you notice I say certain cases because in all of these examples, it's not true that they always admit these, well, they will always admit an elliptic action, but they won't always admit a Hamiltonian action with this finitely many fixed points, which I guess is partly also why Okunkov considers more general fixed point loci. So, you know, you in each case, you have to work out which examples do admit this more restrictive action. Okay, so to present the results I'm going to give, that's all we need in terms of the geometry. But I do want to mention an additional ingredient because it's important in the proof for the result, at least. So just as we did up here, when we sort of looked at the decomposition of lambda into these Lagrangian pieces, you can do exactly the same thing for the elliptic action. So I can similarly look at the set of points x that limit to a given fixed point. Now, because every point in x admits some limit, this gives me a stratification then of the whole space. And one can check that these cells, they're now co-isotropic rather than Lagrangian. But they're really important because they allow us to induct on various constructions to do with these DQ modules. Okay, and so in particular, what one can do for each one of these cells is you can perform a co-isotropic reduction, but in the algebraic setting. So this was our sort of geometric original result. And in this case, with the finitely many fixed points, what you find is that for each cell, you can find some symplectic space, Si, which is really just affine 2n space with the usual symplectic structure, together with a smooth morphism from the cell to this space Si. And it's a reduction. So you're killing the sort of kernel of your form on Ci. And so formally you just say that, you know, the pullback of the symplectic form on Si is the same as a restriction of the big form to the cell.
Excuse me, this cotangent bundle structure, is it canonical?
No. So you're quite right. So this is really misleading in some sense. I mean, this statement is also rather misleading. So maybe I'll talk about this one. So really what this is saying is that you can push down your Lagrangian cell and it's going to give you a choice of Lagrangian inside this Si. But the way we construct Si, there is no preferred Lagrangian and there's no real splitting. So this is somewhat misleading. It's really just, and in fact, it doesn't even have a, there's no vector space structure on Si really. It's just an affine 2n space with a symplectic structure.
Yeah.
Yeah. Yeah, so that's, you know, one can make that isomorphism, but it's certainly not canonical or anything like that. Okay, so that's the end of the geometry. That's all the geometry we'll need. So now I'm just going to talk about sort of classical what's called d omega duality, and this is a type of filtered Koszul duality. And I'm really going to talk about a very specific, a very easy setting, so just on a vector space. And classical d omega duality means going back to differential operators. Okay, so we're going to forget about deformation-quantization for a bit and just talk about classical d modules. Okay, so as it says here, I'm just going to fix some finite dimensional complex vector space. and I'll just write dv for the sheaf of algebraic differential operators on V, and omega sub dr, it's just going to be the sheaf of all differential forms on V, and the key point is this is a sheaf of dg-algebras with the derived differential. Okay, and so the point here is that if you look at this thing, so this I'm thinking of as the derived complex, that's a bimodule over differential operators and this dg algebra omega. And so it gives you a pair of functors between their homotopy categories. Okay, so K of dvq co, right? So this is the homotopy category of quasi-coherent D modules. So quasi-coherent, as we were sort of talking earlier, means with respect to O. And similarly, this is going to be the homotopy category of dg modules over omega, which are quasi-coherent over O of V. Okay. So these are the categories I'll start with. And just taking sheaf hom or tensoring gives you a pair of adjoint functors then G and F between these two categories. Okay. So one would like to say that they give you derived equivalences, but that's not true for the sort of usual derived equivalence. You have to change your derived category in order for that to make sense. And so the key definition is that I'm going to say that an omega module n is F acyclic if when you apply F to it. So remember, F just means tensoring back up to get a D module. What you get is an acyclic complex of sheaves. Okay, so it's known that if n itself is acyclic, then you can check that it's F acyclic as well. But the converse is certainly not true. So there are plenty of acyclic modules over omega which are not F acyclic. Okay, so what one does is one restricts to the subcategory, which I'll write script n of F, of those acyclic complexes which are F acyclic. And then this is some thick subcategory, and so you can localize your homotopy category with respect to it. And I'm not sure this is standard, but I'll call this the exotic derived category. Okay, and the usual derived category for this DG algebra is then a quotient of this exotic derived category. Right, we've made it bigger by killing less. And then the statement of this d omega duality, which was originally due to Kapranov, but I guess in this version I'm giving now, it's really written up in Beilinson-Drinfeld's book, is that these functors descend to an equivalence between the usual derived category of D modules and this exotic derived category of omega modules. And so this is an example of filtered Koszul duality, because one could, of course, equip these modules with filtrations, and when you take associated graded, you pass to the sort of classical Koszul duality between, well, I guess there would be quasi-coherent sheaves on the cotangent bundle and modules over omega, where you forget the differential on omega, take the zero differential. Okay. Okay, so one can try to make this a bit better behaved though by considering O coherent modules over omega. So there's a proposition due to Beilinson and Drinfeld that says that actually if n is coherent over O, so in particular it's bounded and each degree is locally finitely generated, then in fact F acyclic is the same as just being acyclic in the usual sense. And once you have this observation, what you get is that F restricts to an equivalence between the usual derived category of coherent omega modules and the bounded derived category of coherent D modules. And here I mean coherent as D modules, not coherent as O modules. Okay, so there one can forget about this issue of F acyclic and just work with the usual derived categories. Okay. Oh yeah, and just to say, so somehow one way to reinterpret this proposition by Beilinson and Drinfeld is that because I'm working with right modules, the canonical bundle on V is the right D module, and one can interpret the result as saying that if you take sheaf Hom from this canonical bundle to any complex M, and this sheaf is 0, then your original module was, or your original complex was 0. Okay, so this
is kind of generator or whatever.
Exactly, yes, it's okay. It's a very weak form of generator. Yes, exactly. So it's up. I mean, this is why this equivalence has to be somehow fancy. This will fail if you drop M being coherent and bounded, right? They give some concrete examples where if you're not finitely generated, this statement will fail. But nonetheless, it has this sort of weak, form of generator. Exactly. Yeah. So just a comment for sort of experts. So you can ignore this if you've not seen this before. There is this amazing version of the omega duality, which is due to Positselski, which is much more recent. And so his statement says that the category of, the derived category of D modules is equivalent to what's called the co-derived category of modules over omega. And the reason that this is somehow more impressive or better is that this co-derived category is defined for any dg algebra. It doesn't require knowing about these functors f or g. Unfortunately for us, it turns out this co-derived category is not the right one that generalizes to dq modules. So I won't mention it anymore, but just to point out the reason it doesn't work for us is that actually we will work with a different dg algebra. So we have to do something more naive. We have to take the derived complex and just take its dg-endomorphism ring and work with that instead. Now, you usually would say, well, it makes no difference because the omega derived is quasi-isomorphic to this dg-endomorphism ring anyway. So, if they're quasi-isomorphic dg algebras, it shouldn't make any difference. But eventually we realized that the key point is this quasi-isomorphism does not give you an equivalence of these co-derived categories. And so if you want to work with omega instead of omega derived, you have to somehow forget about this co-derived setting and work in the sort of spirit of Beilinson and Drinfeld. Okay, are there any questions on that sort of classical picture? No, great. Okay, so actually what I'm going to do now, I'll go back to our symplectic resolution and go back to considering DQ modules. But what you'll find is I'm literally going to take everything I've just said about d omega duality and just write down the obvious analog in this setting. And the upshot is that it works, essentially. Okay, so like I said, back to deformation-quantization modules. I can take this script X again to be bionic symplectic resolution. So it has these two commuting GM actions on it. And I'm going to say that some perfect complex L is going to be a local generator if it has this weak generator property, right? So taking Homs from L into M is 0 implies that M is 0 if your perfect. So if you're bounded coherent. And just to make things specific, well, yeah, one should make things specific. So I'm going to fix a choice of a bounded locally free resolution of my generator L. And I'm just going to do exactly the same as I did up here. I'm just going to take omega to be the dg-endomorphism ring of this resolution. Maybe a sort of technical note is that for this to work, one should really take GM invariance. So technically, this omega is not a sheaf on X with the usual topology. It's a sheaf on X with the sort of equivariant topology, where every open set is stable under C star, GM, sorry. But yeah, that's not really important. Okay, so that's my omega. And like I said,
the resolution also is kind of a GM equivalent, or
yes, it should. So when I talk about DQ modules, absolutely everything should be equivariant. Yes.
on the
So
GM only.
GM.
Okay.
Yeah, not under the Hamiltonian action, only under the elliptic action.
Okay, thank you.
Yeah, thanks. And locally free means as a W module, so not over anything else. Yeah. Okay, and so like I said, we do exactly the same thing again. So we have a pair of adjoint functors G and F. So G is just Hom from this bounded complex into your object M, and F just tensors back up again. And again, we do the same definition. So we're going to say that some omega module N is F acyclic. If applying F to it gives you an acyclic complex of sheaves. And then it's well, just some sort of formal nonsense that one gets this derived equivalence, where again one has to take this sort of exotic derived category where you quotient out by these F acyclic objects. And so it's quite easy to show that if L is one of these local generators, then F restricts to an equivalence between genuine derived categories, right? So here again, as in the case of d omega duality, I don't have any exotic thing there. It's just the usual derived category. And that's equivalent to the sort of bounded derived category of coherent W modules. So somehow the real content of our work is not that one gets an equivalence, it's rather that there exists on these symplectic resolutions such a local generator. That's really the content. Sorry, before I get to that, I just wanted to make some sort of remark, which is not really necessary, but I kind of find interesting. This equivalence here is extremely general because it's just some nonsense. And so one thing you can do is you can do this without any assumption on L. You don't need a local generator. So you can even take your complex E to be acyclic, right? So you could take, for instance, E to be W maps by the identity to W. That's an acyclic complex. So omega itself is acyclic. Nonetheless, such an equivalence always holds. And the point being that just this N is very small compared to all acyclic complexes. So in that bizarre example, what you get is that actually every object in the homotopy category is acyclic. So literally everything. So if you pass to the usual derived category, you get 0. But if you do this exotic construction, you get something non-trivial, even in that example. Okay. So somehow the real statement we proved, or the content, is in the fact that if you're in the setting of a symplectic resolution, then a local generator exists. But much more than that, one can choose such a generator so that it's supported on the Lagrangian. Okay, and
supported there are two possibilities: scheme theoretically supported or topologically supported.
Oh, yes. Oh gosh, right. That's true. They're not the same in this. So this is like working with microlocal D modules. It's not like working with usual D modules. So they would be schemes
Probably
theoretically.
you think schemes theoretically.
Well, so I'll look at this wrong. So some power of the defining ideal would kill it.
Okay.
Or rather, if you pass to the local ring at any point not in lambda, you get 0. That's maybe the best way to say it.
Okay.
Yeah.
That's strange. Yeah.
Yes. Well, like I say, somehow you don't have yeah, microlocal. I mean, it's a bit like saying with oh no, that's not the same thing. Okay, I shan't say that. Yeah, I don't think it's like classical D modules. We have that stronger result. So yeah. Okay, so yeah, so this L exists, and because lambda is Lagrangian, L is holonomic. So I have not mentioned holonomic before now, but in this microlocal setting, sort of Gaber's theorem still holds. So if you have any DQ module, its support is always going to be co-isotropic. And so the smallest possible dimensional support it can have is when it's Lagrangian support. And this is called holonomic modules. And so the point is one can choose L to be holonomic. Well, if it's supported on lambda, it's automatically holonomic. And so what you find is that you have this DG algebra omega, and I mean, in some naive sense, it's supported everywhere. But when you take its cohomology, you get a sheaf of sorry, not sheaf of DG, a sheaf of algebras sitting on lambda. And in fact, this is even going to be constructible by a result of Kashiwara and Shapira.
Is it just constructible or more than that, like perverse or something?
No, I don't think it would be perverse. Well, let me think. I don't think so. No. No. So, yeah. Okay, so that's the result, and maybe in the remaining time, I'll just very briefly make a comment on one idea in the proof, which is that there's a recouvrement pattern for these holonomic DQ modules relative to these coisotropic cells. So this is why I mentioned these coisotropic cells earlier. So remember, this script X, it's has a stratification by these coisotropic cells where the I labels the fixed points. And so one of these cells will be open, and you can start with that one, and then you can go down by adding cells of smaller dimension. And so you can always sort of reduce to the case where you're considering some coisotropic cell which is closed. And you do the usual thing then, so you form this sort of open-closed diagram. And what we showed was that, at least for holonomic modules, you do have the sort of six-functor formalism. You have this recouvrement diagram, where you reduce to the cell and you restrict the open complement. And this allows us to then inductively construct this local generator starting from the open stratum. And the point is that we proved in our previous work that when you look at these holonomic DQ modules, which are supported on this closed coisotropic cell, that category is equivalent to DQ modules for the coisotropic reduction, which is this S here. So C mapping to S is the coisotropic reduction. But because we're in the setting of finitely many fixed points, that S is really just, well, again, this is a bit misleading. This is just this affine space with a symplectic form on it. And so you're really just reduced to considering D modules, sort of classical D modules, on some choice of Lagrangian inside that. And so there one can apply the classical d omega duality, and in particular this results by Beilinson-Drinfeld, and then you sort of just lift this inductively then through these coisotropic cells. And maybe just very briefly mention somehow this was some motivation for us, even though it's really just an analogy, but there is some much earlier work by Nadler looking at sort of Fukaya categories where he describes some similar kinds of constructions using these sort of recall moment patterns, and I guess he calls it categorical Morse homology. And I guess you could think of this in a similar way. So inductively constructing from very simple pieces these local generators of the category. Okay, so that's all I had to say, so I'll stop there.
Yeah, thank you very much. So, are there any questions? Yeah, actually, I have few questions. So first, you mentioned that you are motivated by a representation theory of some classical algebras like Cherednik and so on. So what's the consequence of this duality for Cherednik? For example, for representations of Cherednik algebras.
Yeah, so unfortunately, we haven't been able to get many consequences. An issue is that we can't really compute these things in explicit examples, like the Cherednik algebra. So even in that particular case of the Hilbert scheme, I don't know what this omega actually looks like at all. So yeah, and I mean, I guess one motivation we had was that we thought maybe this would somehow be related to symplectic duality, which is meant to have a version of Koszul duality in the definition. But there really, it's a Koszul duality between two category O's. Whereas it is true that module supported on lambda is by definition category O, but somehow only L appears there. So yeah, it's a short way of saying we don't know even in that example really what's happening.
Yeah, another thing, it's maybe rather a remark. Yeah, you know, we have this holomorphic Floer theory story with Maxim, and part of it's a general Riemann-Hilbert correspondence, or generalized, which kind of, it's a little bit more general setup, because we start with, say, complex symplectic manifold, maybe algebraic, but not necessarily end out with C star action, and with some additional data at infinity, some good compactification. And then there is a category of these DQ modules so we quantize sheaf, and so okay, there is a category of DQ module, and there is a Fukaya category. In fact, even the family So what you did, you got rid of H bar, and for us it's essential because rescaling the symplectic form, it gives you the local system of categories, and there are some equivalent. Basically, roughly speaking, this category of holonomic DQ modules is equivalent to the category constructed from this family of some global sections of a local system on C star. Yeah, but then if you add one of the two actions, not the one which gives a category O, but the one which is an analog of the Liouville vector field, which rescales the symplectic form. And so then you have this analog of the Lagrangian skeleton. And so you can speak about generators in both categories. Yeah, and on the DQ module side, probably it should be something similar to what you are saying, at least up to quasi-isomorphism. And on the Fukaya category, it's roughly speaking, you take this Lagrangian and you consider endomorphism of it in the Fukaya category. So that's algebra and it's a generator. And there is even better story when you consider something infinitesimally about a fixed complex Lagrangian, possibly singular. And so it's a local version of this Riemann-Hilbert. And it looks for me that it might be very closely related to what you
I mean,
are
if you would
saying.
give a way to compute this omega in some examples, that would be great.
Well, maybe in low dimensionals, you see, that's why I asked you at the very beginning, what kind of representations do you consider? For example, we consider representations which are in a sense holonomic. So like it's not really like what people like finite dimensional representations like but something which rather holonomic. For example, there is a version of our formalisms related to elliptic algebras. It's not on your list, but it's a quantization. It's not a symplectic resolution. It's a quantization of the symplectic surface, which is a product of the elliptic curve and C star, or a version that you have a CP2 and remove a smooth cubic curve and take the symplectic form which has a pole of order 1 on this cubic. So the quantization, it's what is known as Kleinian algebra, and the first example, it's more like related to elliptic algebra. But the classes of representations which appears, it's not like what people like to do, like finite dimensional representations of elliptic algebras, but rather holonomic representations which in some sense have Lagrangian support. And so that's why I asked you in the very beginning. So you get some, at least we got some certainly a relation to representation theory of probably all the algebras which for which the geometric representation theory exists, but some classes people did not consider because it's not everything can be localized. And as for Cherednik algebras, there is one nice example computed by physicists. Maybe it will be of some interest to you in terms of computing the answer in this particular example. I think it's a paper of many people. I remember two of them, Gukov, Sergei
Right.
Gukov, and Karateev, Pyotr Karateev. Well, it's Russian names. It's easy for me to remember. Yeah. And they considered that's what in physics they call it brain quantization.
Right.
But I remember that in the end they arrived to a geometric description of certain, in fact, finite dimensional representations of the Cherednik algebra. And the reason for finite dimensionality was that this Lagrangian skeleton, which they got in the end, it was compact. It's
Right.
rather like, probably it was some kind of resolution of singularities, so it was a bunch of CP1s.
Yeah.
And so that's, but physicists, they are very concrete, precise people. They do not speak about equivalences of categories, but they computed some. So maybe you can indeed, yeah.
Yeah.
So it's
Okay. Yeah, I guess, I mean, you're right that usually people consider category O or something like that, but I guess the reason that this result was surprising is that L is in category O, so it's a very small object, but in some way it's big enough that it sees the whole category.
but that's actually, it's indeed, it's amazing, because from the perspective of our Riemann-Hilbert correspondence, it should see only really holonomic modules, not everything. Yeah, it's amazing. Okay, more questions? Well, if there are no more questions, well, thank you for the very interesting talk.
Oh, well, thank you for the invitation. Yeah.
Yeah.
That was good. Yeah, thanks.
And this is it for today.